Okay, students, we're back again, and I just want, last time we kind of ended up with the concept map, which is, by the way, is a great summary to be able to help you understand sedimentary rocks, and something you should go back to study from as we go through this. However, we're not going to go into some more detail. We're going to start talking about weathering, what actually weathering is, what erosion is, what's class, what's sediment. All these kind of terms that I kind of use loosely here in our first lecture, we'll kind of go into some more detail about, and then we'll walk you through the process and so you'll be able to better understand it. Okay. Some students have a hard time with this. There's a lot of things to bombard you with sedimentary rocks all at once, and to make a lot of the connections in here. I know some of my students who actually do the major think it's even difficult, because we have whole classes on just this topic for the whole course, right? And I've taken courses just on chemical rocks or just on clastic rocks, and so it's a very detailed and pretty prolific kind of topic. But we'll try to go through it the best we can to simplify it for you. Okay. So let's start off with this one here, and that's what's the difference between weathering and erosion. So if I have my granite again, like I had in my hand here earlier, which is an igneous rock from molten material that cooled off in time, that granite might be a fresh look of it might look like this one right here. Okay, but over time, that granite will interact with water and air and stuff on the surface. And slowly those rocks will start weathering away, maybe through chemical processes or physical processes. And so you might get what we call a weathered granite up here, and then new sediment might fall off that granite as it slowly is eroded off of the material. Okay, so weathering is the process in which the rocks at or near the Earth's surface break down. So it's the little breakdown of those materials, whereas erosion is the actual picking up or moving, the initial pickup or initial transportation of the material through different processes. And there's multiple ways in which we can erode material. So a lot of people think of it this way. When they think of erosion, they often think about how a farmer's field loses its soil, right? It's because that soil has been moved or transported, initially picked up and moved. That's the process of erosion. Okay, where weathering is the actual breaking down of that rock slowly over time. Now, what factors will influence how much erosion is occurring, and why? That's a good question. I kind of have it here, but it really comes down to viscosity and velocity. Okay, so I paused it for a second because I needed to get something. But what is viscosity and velocity? Now, most people understand what velocity is. It's a rate, right? It's basically the distance you travel over a certain time period. Okay, so the faster moving material is going to, you have material like water you have flowing over a soil, has an easier chance to actually pick up that material because of the energy required that's included within the velocity there. Now, another thing that actually can cause something to be eroded is the viscosity of something. Now, this is silly putty. For those who've played with silly putty before, if I actually hang it here long enough, you'll notice I'm not moving much. I'm not moving my hand at all, but the material itself is slowly moving. This is what we call a viscous material, something that actually moves or flows, but flows slowly in a sense. It's something that's what we call viscosity. The actual term for viscosity is the resistance to flow. So something that's very viscous doesn't flow very well. And something that is viscous, like air or water, flows quite well. So if something like this was slowly flowing down a hill slope, I mean, it could pick something up a lot easier sometimes than water because it has the force behind it. And we'll talk a little bit more about that as time goes on. But the point comes is viscosity and velocity has a big impact. For example, a good example of this might be air. If I had blow air on something, it's not, even though it has high velocity, it doesn't necessarily mean it's going to be able to pick up that rock that might be on my desk, like this rock right here. Now, if I blow air on it, it's not going to move much, right? But if I get a bunch of water, which is viscous, more viscous than air, and start pushing on it, the force of that is going to actually allow it to go down because the water is thicker, or has a thicker viscosity. Okay, has a higher viscosity, I should say. Okay, so there's basically three main agents or fluids that we think about when we think about erosion. Okay, and it's usually I've already given you two of them, and then one of them is air, right? Okay, then water, and then ice. Now, based off of what I just said, which of these is the most powerful? Which one of these is the highest velocity? Which one of these is the most viscous? Well, ice actually has very slow velocity, but because it's so viscous, okay, if I put enough pressure on ice, it will move like a glacier. Okay, and if it does, it could pick up those rocks and actually, it's very, very powerful. So ice is actually the most powerful. It's also the slowest velocity usually, but highest viscosity. Whereas water has high velocities, but also a thicker viscosity than air. So usually ice is the most powerful, and it could actually move rocks the sizes of school buses, homes, down the mountainside. Now, for example, this is Yosemite National Park, and this is the Half Dome in Yosemite. There used to be a glacier that went down this valley and pretty much carved the whole glacier, the whole mountain out. So now you have this nice U-shaped valley. You can see other remnants of it. Here's some glaciers up in, a model of some glaciers up in my home state of Idaho. And these are all the sediments that were deposited or moved along that glacier, like you see in this glacier in Alaska. Moving these sediments slowly along as they fall off onto the glacier, right? So here's some of those sediments at the bottom. What we call these moraines. They're at the bottom of there as all the glaciers deposit sediment at the very end. Well, they also can carve out mountainsides like they did here, or this is actually the Matterhorn in the Alps, and you can see how the rocks moved along the bottom of this surface and just carved and made grooves in the mountainside itself. So it can actually do quite a bit of erosive power. Now, water still has that safe capacity as well. The faster it goes, the more materials or bigger materials it can actually carry. And so you can see this one. This is the Yellow River in China. And you can see that it's called the Yellow River because there's so much sediment in it that has this yellow hue to it. Just like if you look at the Mississippi River, it has a brown hue to it because it has so much sediment in it, right? Now, our river down the street here, which is the Lumber River, is what we call a black river. And it's not necessarily the sediment that's making it black. It's the organic material within it and the acids within that water that make it black. So there's a different reason for it. But usually the coloring within the water has to do either with sediments in it or ions in it. Okay, organic materials or inorganic materials. Okay, and so that material might actually roll along the bottom, what we call the bed load of a river, or it might be suspended up in the water column, which is what we call the suspended load of a river. Right, and this can happen at a beach, a river, a lake, a lot of different things, but that can flow and move that water slowly over time. Our beaches are really remnants of this erosive power of water. Now, wind also can actually cause erosion as well. Think about sandblasting in a sense, right? When something gets sandblasted, often it might be so abrasive, it would get that sediment, push it with the wind, and then slowly take like paint off of a wall or something. Now, usually wind can't or air can't pick up very large materials, so it only can pick up the smaller material, so it has less erosive power in the end. Okay, so then we have what we call weathering, and we're going to talk about the different types of weathering. We're not going to go into the details of each type. Your text goes into more detail than we're going to do in a lecture, and therefore we're going to let the text teach a lot about this, but we're going to kind of hit the highlights of them as we go through this. Okay, so the first one here is what we call frost wedging, which, by the way, is the most common type of weathering there is out there. Mechanical weathering that there is out there. Mechanical weathering is the process in which the rock or mineral is broken down through physical processes. Frost wedging is a great example. What might happen is water might get into a crack, like the cracks that we have here. Now, water, when it freezes, expands, right? And so it might get down in that crack, and then when it freezes, it will expand, pushing the rock apart. Now, let's say it actually melted, that water melted, that ice melted, and then more water were able to get back down to that crack that you just formed. Well, then it freezes again and can go apart more. So this wedging is a slow process, especially if you have multiple freeze-thaw cycles. It can actually start breaking apart rocks. Now, where in the world might you think that you have a lot of frost wedging? Well, it's going to be in a place where you have lots of changes in climate, okay, or frost cycles. So, for example, here we're not going to have a lot of frost wedging in our neck of the woods. But what about Antarctica? Well, Antarctica is so cold all the time that it doesn't freeze-thaw very often. So you don't get it very much in there. But places like New York or Pennsylvania, places where you have, or my home state of Idaho, is a great place for frost wedging to occur, because I remember when I grew up, we would have times when we would have freeze and thaws multiple times in a day, which means that you'd have lots of expansion and contraction of the rock and the water. Another one is crystal growth. So if you get, for example, salt in that crack, and that salt will start to expand as it grows, will actually push apart the rock as well. You have thermal expansion and contraction. When something gets hot, it expands. When it gets cold, it actually goes back down to smaller size. So it goes bigger, smaller, bigger, smaller. So now a rock can do that slowly over time. So this is an example of one where you've had thermal expansion slowly over time. Now in forest fires, this is amplified, where the rocks can start shedding off the outside portions because it's cold, hot on the outside, colder on the inside, and therefore they expand at different rates, and they come off like in these little sheets, like little onions, right? Exfoliation is one where you have a rock that's under a lot of pressure, and then it's brought up slowly over time, and then that pressure is released, and so it expands, finding similar to this right here, where it will form off into these different cracks. Root wedging, or biological activity, is a big one, where the plants themselves or animals will bore down into the rocks, break them apart to actually form the same thing. So the plant gets inside the crack, wedges it apart, keeps growing, and does the same thing. Abrasion, this is an example of abrasion, where wind or water will flow through an area and slowly move sediment along with it and abrade the other sediments around it to form a type of mechanical weathering, right? Whereas chemical weathering is not from the physical breakdown of materials, but it's the actual process of chemical reactions interacting with the rock. Okay, so the actual mineral or rock is altered due to some kind of a chemical reaction. So the three main types that we do, and this, once again, I'm not going to go into details of these because they're in your text and go into more detail there and in your assignments. First one is dissolution. That was one you probably very common or understand quite well. Example, if you put salt in your water for cooking your pasta or whatever, or if you put sugar in your coffee or whatever you drink, it will dissolve, right? Well, some rocks will actually dissolve around water as well. So, for example, rainwater is naturally acidic, and so it slowly will dissolve some rocks, forming caves or things like that. Okay, so this is an example of like acid rain that can do to some marble and other statues that can slowly dissolve something away. Oxidation is the breakdown of the iron within a rock, and so the iron will actually break down, will react with the oxygen, and so therefore will be extracted out of the mineral and into a form of some type of rust. So you can see that within these sediments here in the southwestern United States. Hydrolysis is another example here. This is usually when water is interacting with some kind of a feldspar or some other minerals that are not as stable as like maybe quartz or something like that is, and the water will interact with the mineral and then alter it into a clay of some sort. So this is a great example of this is if you've ever been to Yellowstone National Park, there's all these little mud pots because the heat will amplify the interactions, and therefore there's these basically bubbling mud coming out of the ground because of this hydrolysis as the water interacts with the rocks, right? So when you have this weathering, the more surface that the water can actually interact with, or braid or whatever, the more you're going to have the rock break down. Okay, so imagine a peanut M&M. I had one on my desk just a bit ago from another colleague of mine who gave me some. And what you'll notice here is if I put this in my mouth, okay, it would slowly dissolve, right? Slowly dissolve. But over time, the candy would dissolve, maybe the chocolate would dissolve, and then what you'd have left is the peanut. Well, This would this would go even faster if I broke it up into small pieces. Now we have tons of surface area and then have it dissolve. Then it would break down a lot faster.